Hello, this is part two of the replacement recording from yesterday. We're looking at datagrams and the structure of datagrams. So, as I said at the end of the last clip, a packet in the IP layer is called a datagram, which is variable length consisting of two parts. Firstly, a header and a data area. The header is 20 to 60 bytes in length and contains information essential to routing and delivery. So very, very important. Right. So let's have a look at the let me have a look at the structure of an IP packet, an IP datagram. It's this. Uh, Here's the header, followed by the data area of the packet. The header is between 20 and 60 bytes long, and in virtue of the fact that the total length field in the header is 16 bits long, it means that the maximum length of the entire packet, uh, including the header, is 65536 bytes long, which is 64 uh, megabytes. Right, so it's quite big. And let's just look at these various fields. So beginning at bit 0, there are five 32-bit chunks at least making up the header, and these 20 bytes of the header, it's called the base header. It's the base header. Now let's have a look at some of the fields. Version number of IP, the header length given by 4 bits, something called a differential services field, which I'm not too bothered in discussing here, the total length field, then a 16-bit identification number. Initially, it's completely random, 16-bit number. It's called the identification field, followed by 3 bits, the flags, and this field has got everything to do with fragmentation. And fragmentation is going to use the identification field as a way of identifying um, an IP packet together with all its fragments if the original packet is fragmented. And I'll explain this in a minute. Then we've got a fragmentation offset, 13 bits long, and you'll come to understand why 13 bits are needed, again in a few minutes. Then this byte is representing the time to live field. 8 bits represents the time that the IP packet is allowed to live on the internet. Has a finite amount of time to live. Then specification of the protocol, 8 bits to specify the protocol carried by the IP packet. So when a remote receiver receives the IP packet, it can inspect the protocol field and say, this IP packet is carrying a TCP packet, so I'm going to deal with that appropriately. Then there's a 16-bit checksum, just to keep a check on whether or not any of the bits within the packet have been corrupted, in other words, flipped. Then a 32-bit source address, IP source address, and followed by 32-bit destination address. And following the base header, you might find an extra up to 40 bytes of options fields, and I'll I'll give you a top level uh, description of what the options fields are all about. Quite interesting. Quite interesting. So, just moving on a little bit, we've seen that the header length field here, 4 bits long, and it just means that the maximum header length is 2 raised to the power of 4 minus 1 times 32 bits divided by 8 to give you bytes, and that results in 60 bytes. So up to the maximum length of the header is 60 bytes. So normal size is 20 bytes unless options are included. The most significant bit is numbered 0 on the left, and the least significant bit is numbered 32 on the right hand side. And the way in which the packet is going to be transmitted is that, first of all, 4 bytes in the 32-bit field is transmitted as follows: bits 0 to 7 first, then 8 to 15, then 16 to 23, and finally bits 24 to 32 at last. And this way of transmitting the packet and the packet header is called big endian, and it's also called network byte order. Machines that store data otherwise are called little endian, and it must convert header values into network byte order before you can actually do anything interesting. So looking at the service type or different DS field, so let's have a look at the DS field. 8 bits DS field, and I'm not terribly interested in this at the moment, and I'm interested in these particular, looking at these 4 bits, and if this bit is set, means please router, try and minimize, please minimize the delay. If the T bit is set to 1, it's telling a router to try and maximize the throughput. If the R bit's set to 1, just try and maximize reliability, and otherwise this bit might be set to 1. It just says minimize the cost of communicating this and other similar bytes. I'm not looking at the code point interpretation of those bits. So the next 4 bits that we've just looked at are called the type of service bits that we're expecting. Okay, that's quite interesting, but it's a discussion for another time, I think. Types of service, as I've already told you, are these. If the bits are 0, 0, 0, just accept the default service offered. If you want to look at the RFCs, look at 1340 or 1349, which corrects 1340. Default types of service. If you're using ICMP, the type of service bits will be set to normal. If you're using FTP, you're transferring files, you want to maximize throughput of data. It's important that you send as much data as possible, as quickly as possible. And if you're doing sending mail, again, if you're sending mail, then maximize throughput. But a mail packet might be used to send a command to the mail server, in which case you want to minimize the delay that the command gets to the server. But okay, that's giving you an idea of what's going on. Type type of service bits aren't supported by most TCP implementations, though one does enable you to set that, and that to me makes a lot of sense. So just skipping the next couple of slides. Note that the total length field defines the total length of the datagram, including the header. And as I said in the first video script, all you need is to know when a packet's about to arrive and its total length. You don't need anything corresponding to a stop bit or a particular end of packet sign saying that this is all I've got to give you. Right. So using this field and the header length field, we can calculate where the data part of the datagram begins, because you know that it's got to start after the header ends, or header plus options ends. Since this is a 16-bit field, the maximum size of the IP datagram is 65535. And this field changes when the datagram becomes fragmented. Right, and just a little explanation of where I got 65535 from. 2 raised to the power of 16 minus 1 gives you that figure. Right. The time to live field is required in the header, since some data links pad small frames out to be a minimum length. So the first part of an IP packet's journey will be its transportation using perhaps Ethernet. So if you've got a very small IP packet and it's less than 46 bytes, then Ethernet is going to pad the IP packet out to 46 bytes. IP datagrams logically can be as small as 20 bytes. And if the TL field was missing, IP wouldn't know how much of a 46 byte frame is actually part, or the data part, of the IP datagram. Okay, so the idea of encapsulation or riding piggyback is extremely clearly illustrated by this diagram, together with the problem with Ethernet. So an Ethernet packet is going to consist of a header followed by the IP packet. And the IP packet could be smaller than 46 bytes, in which case there's going to be some padding bits added to make it up to 46 bytes. That's then going to be followed by a trailer, the end of the Ethernet packet. There's an explicit bit sequence marking the end of the packet that's just been transmitted. So can talk about multiplexing of all the protocols which are being carried piggyback by an IP. Here's an IP packet, and here's the header of the IP packet, and what goes in the data field of the IP packet are complete TCP or UDP or IGMP packets. So it's called multiplexing, or encapsulating one protocol inside another. So that's reasonably clear. Time to live packet. Each datagram has a finite life, and originally this field contained a timestamp that was decremented by each router visited until it became 0, and then the datagram was discarded. And the idea of a time to live field is that you don't want an IP packet staying in the internet forever, right? So every time an IP packet is routed, the router is actually going to subtract from the time to live file. And typically, these days, it's set at twice the number of possible routes to the destination. And the idea is it prevents infinite journeys, which did apparently used to happen. And the time to live field also might be used for security purposes. For example, if you don't want packets to leave your network, you might send the time to live field to say 5 if your network has just 5 routers. And that'll avoid it escaping from your network and falling into enemy hands. So protocol fields can contain bits representing the protocol that's being carried. For example, if you find a 6 in that field, check the field, go back to the diagram. If you find 6 in the protocol field, it means that your payload is a TCP payload. So I include some examples here which are quite useful. If a packet has arrived with the first byte that looks like this, 01000010, the receiver, the router, or the actual intended destination will discard the packet Y. Well, there's an error in the packet. The 4 leftmost bits shows the version, which is okay, but the next 4 bits shows the header length, which means 2 times 4, 2 times 4, alright, 2 times 4, which is 8. And that's wrong, because the minimum number of bytes in the header's got to be 20. Therefore, you can conclude that the packet has been already corrupted in its transmission and should be rejected. Okay, example 2. In an IP packet, the value of the header length is 1000 and binary. How many bytes of options are being carried by this packet? So the header length is 1000. So it's 8, which means that the total number of bytes in the header is 8 times 4, or 32 bytes. So the first 22 bytes are the base header, constitutes the base header. Therefore, the next 12 bytes are, or represent, the options fields. So in an IP packet, the value of the header length is 5 hex, and the value of the total length field is 28 hex. How many bytes of data are being carried by this packet? Well, you can calculate that. If the header length is 5, means that the total number of bytes in the header is 5 times 4, or 20 bytes. No options. The total length is 40 bytes, which means that the packet is carrying exactly 20 bytes of data. Okay, so from the point of the receiver, the headers fields are quite important for checking and understanding what's being transmitted. So if an IP packet has arrived with the first few hexadecimal digits as shown, how many hops can this packet travel before being dropped by a router? And the data belongs to what upper level layer protocol? Well, to find the time to live field, we skip 8 bytes, in other words 16 hexadecimal digits. And the time to live field is the 9th byte, which is 01. 01. This means that the packet can only travel 1 hop. It's got a very restricted field of movement. And the protocol field is the next byte, which is 02. So maybe I've got this wrong. I haven't done my calculations properly. This is the that is the time to live field, and this is um, the protocol field, which is 2, which if you go back to the table, it represents a protocol of type IGMP. So we're just going to do a little bit more before finishing. Right. So we're looking at the identification field, which you'll remember is 16 bits long. And the identification field contains a number which uniquely identifies each IP datagram sent by a host. Normally, this number is going to be incremented by 1 each time a new datagram is sent. So let's just have a look at. We're going to have a look at fragmentation next. And what I've done so far is to look at most of the fields in the IP header, and I've explained their purpose and function. And it involves being able to determine where the data starts to, etc., etc., etc. So we're now looking at fragmentation, and the format and size of a frame depends on the protocol used by the physical network, because a datagram might need to be fragmented or reduced in size to fit the protocol regulations. So first of all, I'm going to talk about the MTU. So routers often have MTUs associated with them. It's the maximum transmission unit. Okay, maximum transmission unit. Just to remind you, the 3 relevant fields that we're going to look at now to discuss fragmentation is identification, the flags bit, and the fragmentation offset, which is 13 bits long. Alright, so what is... Okay, well, let's think about maximum transmission units first of all. The idea is the IP datagram should be encapsulated within, say, an Ethernet packet, and that has a maximum transmission unit associated with it, the maximum length of data that can be encapsulated in a frame. In other words, it's the maximum length of for example, an IP packet followed by the trailer. So a host isn't required to receive a datagram larger than 576 bytes, and that is specified by the Internet, I think it's the Internet Engineering Task Force. TCP divides the user's data into pieces or chunks so that this limit can be respected and observed. With UDP, many applications that we will study limit themselves to 512 bytes of user data in order to stay below the 576 byte limit. So in practice, most implementations, for example, for most implementations, allow for just over 8,192 byte IP datagrams. And Ethernet has a maximum transmit unit of 1500. Telephone protocol (PPP). It's got to be under 296. Something called a hyperchannel. It's 65,000, around the order of 65,000, and so on. Going back to the flags field, there are just 2 bits. And if the first bit is set to 1, it's telling a hardware unit, please don't fragment me, I'm not allowing it, don't do it. On the other hand, if the M bit is set, and this is 0, it simply means I'm an IP packet with a particular identification number. There are going to be more fragments of IP with the same identification number to follow. So let's think about the logic of fragmentation. So first of all, I want you to notice that fragmentation can be performed by a host or any router on the path to the destination machine. And reassembly will and can be done by the receiving IP station, the receiver's IP software. So I'm just going to look at the abstract method. I'm going to simplify it a little bit to demonstrate the idea. And it's this. You break a chunk of data into smaller chunks of size s. And what I'm going to do is to assume that each chunk is going to be equal to or less s bytes in length. And what do we need to do in order to make reassembly possible? Well, let's supposing we need to send just 30 bytes. And the maximum transmission unit for sending is 4 bytes. So 4 is actually going to 37 times remainder 2. I think, I think that's right. So what I need to think about is sending 30 bytes that looks like this, a chunk of 30 bytes. So I need to fragment that. And what I can do is to send the data in 7 lots of 4 bytes plus a further 2 bytes. That gives me the 30 bytes, original 30 bytes. So we can first of all label bytes by the number in the sequence that the bytes appear. So look at that. We can first of all label all bytes by the number in the sequence that the bytes appears, as in the diagram above. So if I send with each 4 byte payload the original position of the first of the 4 bytes, then the receiver can effectively reconstruct the original byte sequence. So just have a look at this. Here are my 30 bytes, and here I've got a chunk of 4 bytes followed by another chunk of 4 bytes, and this in fact is the 9th chunk. So I've got 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 9. This is the 9th. Sorry, this is the 9th byte. It's the first byte of the 3rd chunk of 4. So the following data could arrive in any particular order, because remember we're dealing with IP and it's not determined what their order of arrival is. I mean, the last might arrive as the first, for example, an extreme case. So what I've done, what I'm showing here are various chunks of 4 bytes. I don't think I've included them all. Oh, maybe I have. 1, 2, 3, 4, 5, 6, 7. Okay, so I've got 7 chunks of 4 bytes, and I'm labelling each with the number of the first byte as it occurs in the original sequence. So have a look at this. Let me get my cursor. This is the 3rd chunk of 4 bytes, and it's labelled with 9. 9 is the first byte. Here it is again. I've got a chunk of 4 bytes, and the first byte is given its original position in the original sequence of bytes to be transmitted. So if you think about having this information, so I've got 7 chunks, each labelled, I can easily reconstruct the original sequence. So, for example, byte number 20, this chunk whose byte was number 25 can be fitted, I think, here. One, two, three, four. So I put, what am I talking about? This is, sorry, this is 20, this is number 25. This is a chunk of 4 bytes of data whose first byte is labeled 25. That goes here. One, two, three, four. Oh, no. One, two, three, four, with a remainder 2. And this chunk of 2 bytes will fit here, absolutely. So it's a bit, going back to the idea of lossless information. We've actually, well, we're not compressing anything here, but we've got a lossless mode of transmission of an IP packet that has been broken up into different chunks that are arriving at different times. We can reconstruct the original information very easily. So I'm going to end the presentation there. I mean, I've given you, in total, 2 presentations give you about an hour's worth covering the main topic, and I think I'm going to make a third video clip just indicating what the overview of Friday's morning session was, and talk a little bit about our approach to Java, and hopefully it'll give comfort to those students who perhaps, because I don't know, perhaps haven't done any programming before, but everything's under control. So hope you continue to have a very good weekend. Here in the mountains of Wales, it's a beautifully sunny day with a clear sky. There are lots of baby lambs, spring lambs, together with their mothers, and the mothers are being quite viciously aggressive and protective of their babies. So if I go for a walk, you have to meet some hostile sheep. So with that thought, I'm going to finish. And I'll hope to see all of you with me next week. Goodbye.